Recording is not started.
Huh? Amrita, what is that?
Nothing, sir. Just now you started the recording. No, sir.
Yeah.
Yes.
So it is lecture number 1. Unit number 4. Okay, so subsystem design and subsystem design. So here we are going to talk about mostly the circuits only, implementation of the different logical circuits with the help of transistors. So far in previous semesters, we have seen that implementation of the circuit by using the gates that we have seen. Okay, so by using the NAND gate, NOR gate, maybe AND gate, OR gate, we have realized the circuits, or we have implemented the circuit. But the question is that in our course, we are going to implement the circuits only by using the transistors, right? So what are the questions, what are the things that we need to talk about here is, first of all, gated logic, gate restoration logic. So gate restoration logics that we are going to look at. And the second one is switch logics. Switch logics. Okay, so what is the basic difference between these two logical implementations? Is that we are going to apply the input. We are going to apply the input at the gate of the transistors. Okay, if you apply the input at the gate of the transistor, such realization we can call it as gate restoration logic. Whereas in the switch level logics, okay, we have to apply the input at the source or drain terminals. Okay, therefore, so normally this is what we look at. So this is where if you are applying the input here, so this is called gated logic. Suppose if you apply the input at this place, for example, input at this place, then we can call it as switch logic implementation. Switch logic implementation. Okay, so we take switch logic implementation after some time. First, we talk about gate restoration logic. The generalized architecture for gate restoration logics are as shown. So as we know that we need to have one network that is called pull-up network. Another network we need to consider that is called pull-down network, right? So these are the two networks that we have to consider in case of gate restoration logics. So what we have to do, we have to apply the pull-up network to power supply line VDD. We have to apply ground line to the pull-down network and take a common point. So connect these two things and take a common point. Connect these two things and take a common point that is called an output. Okay, and we have to apply the inputs at the for this particular pull-down network. Okay, so we have to follow. This is the approach. So these are called inputs. These are called inputs. Okay. So this is what the generalized architecture that we have to follow. One of the important point to remember in this generalized architecture is that the first one is usually what we do, pull down network is realized by most of the cases NMOS transistors, NMOS and MOSFETs, right? Whereas this pull-down network, pull-up network, pull-up network is decided depending upon the technology. Depends on technology. Okay. Or a function of technology, or we can write it depends on technology. Depends on technology. So, for example, if you use if you use NMOS technology, for example, NMOS technology, pull-up network is actually depletion NMOS. We have to use depletion and MOSFET. For example, it is a CMOS technology. CMOS technology, we have to use enhancement and NMOS. Enhancement NMOS. Sorry, enhancement PMOS. I'm extremely sorry. Enhancement PMOS. So this is what we have to remember. This is the 1 point, 2 points that we have to remember. Another important point is that the output is always inverted output. The output is always inverted output. Inverted output. Whatever the function you give, so the function is overall complement you can see at the output. So this is the generalized nature of the gate restoration logic implementations. Whenever you do the gate restoration implementation, we have to follow this kind of approach, right? I hope you understand this, what is the generalized architecture for implementation of the circuits. Okay, now let us implement a few circuits. Okay, then we'll move to the examples. For example, I want to implement, for example, y is equal to a dot b whole bar. So as you know that is an AND gate. Let us implement by using a simple NOT gate. First of all, we do it. Okay, simple exercise is that a complement I want to do it. Y is my output. A bar is my y is my output, which is actually defined by complementation of the input. Okay. So how do we do this one? By using NMOS technology, let us write first. So compulsory there will be a question in your examination for implementation of the circuit. Maybe 6 marks or maybe 12 marks will be there. So please concentrate on this one. Very easy. The first one is NMOS technology. So NMOS technology, if you are using, means pull-up network must be depletion type mode transistor. So depletion stands for, this is what the symbol that we have to use. Okay, that means thick line that we have to use for this. Okay, it's so awkward. So we write again. Some thick line that we have to write. Okay, and this is how we write. This is a depletion. Pull down network must be NMOS transistor, that to enhancement. So this is how we have to write. So therefore, the symbol also must look good. So don't write just like that. Okay, and take the connect these two things. Okay, and take a common point here. So the VDD is on the ground. Okay, this is connected to this one. This is, it must be always on. And take a common point. This is called Y. This is called A. So therefore, what we can here, you get it here. So this implementation always gives you a complement. Whatever the input is there, that will be complementary over here. So its operation also we have already studied carefully. We have already studied, but let us see the operation once. Okay, operation. What is operation? So in order to understand the operation, you should remember 2 points. One point is that if it is NMOS transistor, if you apply logic 0, it becomes off. It is an open circuit. If an NMOS is filled, is logic 1, if you apply at the gate, then it will be short circuit. It will be short circuit. It will be short circuit. Okay. Similarly, if you understand that if a PMOS transistor, logic 0, if you apply, it is a short circuit. Remember this point. In a switching point of view, we are talking about. Similarly, if you take a PMOS transistor here, logic 1, if you apply, it is acting as open circuit. So these fundamentals you should know. Okay. These fundamentals you should know. Okay. So let us apply the same concept here. Okay. Since this depletion mode transistor is actually connected gate and source, even the gate and source are at the same potential, generally NMOS transistor becomes off. But depletion mode type enhancement mode transistor becomes off. But the depletion mode, it becomes on. Channel is already present. So therefore, we estimated that the VDD is available here, and this is actually acting as a short circuit. Okay, it is already on. On we can assume that on means assume that that is in short circuit manner. Okay, now what about this bottom transistor? Let us apply logic 0 here. So the case 1 is case A is equal to logic 0 applied. Okay, so in that situation, the PMOS transistor becomes off. Take a common point here. This is called Y. This is called Y. Now, what is the Y value? As we know that.
Sir, PMOS will be off for 1 month. Sir, for 0, PMOS will be on now, sir. Like short circuit mostly.
No, it is actually NMOS transistor I have given. If I am NMOS transistor, for NMOS transistor, if logic 0 is applied, it will be open circuited. Okay, so this is what I'm applying at this place. So I'm applying here is logic 0. So if I'm applying the logic 0 for the NMOS transistor enhancement, it will be off. Now, so this is actually a short circuited here. So you observe it's a short circuit, right? It is a short circuit. What do you mean by a short circuit? Means that means the potential drop between VDD minus of Y is equal to 0. The drop between this one is equal to 0 stands for a short circuit, which means that Y is equal to VDD. Y is equal to VDD. VDD stands for logic 1. That's what in the logical sense it is logic 1. Right? So that's what we observe. The next one is case number 2. That is, we apply the logic 1 here at the gate. So I think it's not a good way to write like this. Case 1, which implies that A is equal to logic 0. Case 2, which implies that A is equal to logic 1 or VDD. Okay. In this sense, what we do, what we know that here we observe that VDD is there and ground is there. VDD is there and ground is there. So here we observe it is always on, but here this is also on. This is also on. Bottom transistor is also on. So these two things are connected here, and this is a common point is Y. So the question is that whether the output is connected to ground or whether the output is connected to VDD. That's what the question is. Okay. As you know that it is actually it is connected to the it is always pulls down by the ground, then that other pulls up to the this one, because the resistivity of this depletion mode type of transistor is more than that of the enhancement mode type of transistor. Therefore, the Y is pulled down by the ground than that of the pull-up to this one. But there is an effect is there by the pull-up network. Therefore, it cannot allow you to go to the Y is directly go to the ground directly. Okay, that means some kind of non-zero ground value will be there for the Y. Okay, because that is what we have seen previously. Okay, so it cannot go directly zero because it is affected by the pull-up network. So, but anyway, we are approximating this one is actually to ground value. Approximating this value is to ground value, which means that we are getting the output Y value is equal to logic 0. So whenever I'm applying the logic 1 here, logic 1 here, logic 0 I'm getting. Whenever I'm applying the logic 0, I'm getting logic 1. Therefore, it is called simply an inversion operation. It is simply an inversion operation. Okay. So let us apply the same concept if you are CMOS technology. Okay, let us consider the CMOS technology. Okay, so what we can do here is that if CMOS technology means PMOS transistor is required at the port at top. PMOS, bottom one is an NMOS. It is important to note that whenever we are implementing a circuit by using the CMOS, we have to remember some points. So what are the points that we have to remember? We need to remember some points. So NMOS, number of NMOS transistors, NMOSes must be equal to the number of PMOS transistors that we have to take. That is the first point. Okay. What is the second point we should do? So for NMOS, if we take series connection, in PMOS we have to take parallel connection, parallel, and vice versa. So vice versa. Okay. That means that if NMOS is in parallel, that means in the parallel, it must be in series. Okay, that's what we remember, these 2 points. These 2 points are essential for this one. And another third important point is that short circuit inputs. Short circuit, or I can say that connect the inputs. Connect the inputs. So these are the So these are the 3 points we should know. So what I have considered here, since Y is equal, what is my function is? Since Y is equal to A complement, by looking at this A, the number of transistors can be decided. So how many number of transistors are there in the pull down network? First of all, 1 transistor. So how many transistors we have to take at the pull up? Also 1 transistor. So since 1 transistor means series and parallel connection is invalid statement, so I don't do that one. But the third one, connect the inputs. So we need to connect the inputs here. Okay, and take a common point, and take a common point here also. If you write A here, Y will be generated. That becomes A complement. That's what is happening here. So now let us see the operation. What is this operation? The operation is that when Van is equal to 0, sorry, the case number 1 is if A is equal to 0, what will happen? For the PMOS transistor, on, right? So from the VDD, the PMOS transistor is on, therefore it is acting as a short circuit. It is acting as short circuit. Short circuit. What about NMOS transistor? It's off. It is off transistor. So what is the common point here? It is nothing but Y. So Y is connected to VDD, as we know that very well. We know that VDD. Now similarly, if you write A is equal to 1, for example, if you write A is equal to 1, this PMOS transistor becomes off, but NMOS transistor becomes on. NMOS transistor becomes on, right, like this. So I should take a common point. This is the common point. Okay, this is called Y. Y is connected to ground, exactly equal to the ground it is possible. So therefore, which means that this is a logic 1 here, which means that it is a logic 0 here. So 0 applies to 1 actually, 1 applies to 0. So this is how we need to verify the output, right? So let us apply the NAND operation by using both. Okay. Quickly, let us move to this one. NAND operation. For example, Y is equal to A dot B whole bar. So in NMOS transistor, what I have to do? NMOS technology. NMOS technology. Next one is CMOS technology. I'll write. So since we have got two variables, right? We have got two variables, A and B. So for two variables means two transistors we have to consider, but that too in connected in dot notation. Dot means series connection. We have to take a series connection of the two transistors. So we can take either A here or B here, or upper one is B or bottom one is B or A also. It's not. It is possible. The next upper transistor is actually a depletion type mode transistor. Depletion mode type of transistor. This is connected to VDD. This is connected to ground. And take a common point. It is called Y. So Y is actually A dot B will be the answer. So, but provided that we have to remember that these two are connected. Okay, if these two are not connected, it's not correct. Okay, very simple. Similarly, what you get here is that so NMOS transistors we have to take as it is. Okay, series connection. Whereas PMOS transistors, what we have to do, we have to take opposite connections, right? We have to take opposite. So that means PMOS transistor, but to that they are connected in parallel. So please remember, these two are connected in parallel. Okay, so I hope you understand the situation. This is called VDD. This is called ground. So connected here is A, for example, this is a B. Okay, you can also write it A here and B here. Okay, A to A connected, B to B connected, but in a circuit point of view, it is sufficient to by applying the inputs at that particular place. But when you draw the stick diagrams, when you draw the layout, it's not like that. We have to connect A to A, B to B. Okay, and take a common point that is called Y. Y is equal to A dot B whole bar. Right, this is called CMOS NAND gate. Okay, therefore Y is called, what is the Y here? Y is A dot. Okay, I have already written, right? Okay, no problem. And so let us talk another one. For example, y is equal to AB bar plus A bar B. AB plus A bar B whole bar, for example. Whole bar I don't want to raise. Okay. By the way, what I have to do is, for example, I want to write it for y is equal to AB. Suppose y is equal to AB, I want to have. Not whole bar is not there. Then since if you are using the generalized architecture, having the pull up and pull down network, it always gives you the complementation. So if you want to have A dot B, just we have to place one inverter here. That inverter must be realized by using the, if it is NMOS realization. If it is a PMOS realization is required. Sorry, CMOS means CMOS realization required, and it is required. Are you getting what I'm saying here? So I think better in it right, otherwise you will get confused. For example, I want to have an AND gate, for example. So copy. I want to paste it here. I want AND gate is required. So AND gate means not we have to provide it there. Okay. So that means that I have to consider this one. I have to consider this one. Okay, so obviously this will give you the only the output only. The output is in the form of A dot B only. So let me consider this is called Y bar. So the better write it as Y1. If I want to get Y having A dot B, for example, A dot B, I need the output of this one is connected from here to here. Output this one is connected from. Right? So this is only the option. There is no other alternative in a case restoration logics. Similarly, for a CMOS means what we have to do for CMOS means we have to take this structure. We have to take this structure. Okay. Place it here. And NOT gate is relevant to this particular one is this NOT gate. Okay, this NOT gate is required. NOT gate is this one is required. So depending upon what technology we have used, the devices also we have to take from that one only. Okay, just we have to connect these two things, that's all. These two things must be connected, right? So remove all these things. It is called Y1, for example. So it becomes A dot B. Is the point. That's how we have to do it. So therefore, Y is equal to A dot B is required, something like this. So you have to understand this concept clearly. Otherwise, because easily you can get scored from your examination. Okay. So it is NMOS technology. NMOS technology. This is CMOS technology. Now, yeah, the time is up. I think you have to go to the next one. But I'll give you some, just 2 minutes time. You give me 2 minutes time. We will do this one also because it is very occasionally in the examination they're asking A dot B whole bar plus A bar into B. So that's what asking. Okay. So from this equation, we can directly understand that it is possible to write something like this: AB plus A bar dot B bar whole bar, right? Am I right like this? If it is possible to write, you can write it there. If you're not able to if you're not possible to write, then don't write and do it. You use the inverter afterwards. Okay. simply not, actually I have given XOR gate actually. This is an XOR gate. So XOR gate is nothing but XNOR. XNOR complement is nothing but this one only, right? So that's what I'm doing. So now the question is that how many number of transistors I should consider? So for this one, how many variables are there here? So 1, 2, A bar, B bar is there. Okay. So you understand that for this particular, this is the one particular product term. This is another product term. Okay. These two product terms are in parallel connection. Okay. Therefore, depend in one particular product term, how many number of variables are there, those many number of transistors we have to consider. Okay. So therefore, what I'm going to do here is that first product term consider two variables. That means two transistors are required. So let us consider first I want to realize a pull down network, something like this. Okay. So therefore, this is called A, this is called B. Now, another product term is there, which consisting of A bar and B bar is there. So I have to consider another transistors, something like this. But look better, I'm going to write in this way. A bar, B bar. Okay, so this left side one is one product term, right side is another product term. These two are connected in parallel, right? These two are connected in parallel. These two are connected in parallel. Okay, so the same structure we have to use. Copy, and then I want to paste it here itself. Paste. Okay. So what I have to do is that instead of NMOS transistor, PMOS transistor, I have to consider, right? Okay, it's not good way that we have to write. What I have to do is that PMOS, this A and B are connected in series, right? We have to write it in parallel there. So therefore, I need to write parallel connection of these two. Okay, right? Parallel connection. So this bottom A bar, B bar is connected in series. Therefore, we have to take it parallel connection there at the top. So write parallel connection of those. How these two are connected? In the bottom, it is connected in series, parallel. In top, it is connected in series. Bottom, these two sections are connected in series. That's it. So take a common point here, take a common point here, connect it here. This one is connected to VDD. This is connected to the ground. Take a common point that is called Y. So this is called, for example, A. This is A. This is A bar. This is A bar. Just we have to connect A to A, B to B, A to A bar, B bar to B bar, something like this. So this is actually acting as A dot B plus A bar dot B bar whole bar. So which is simply nothing but AB bar plus A bar. That's all. So this is how we have to implement exclusive OR gate by using this one. By the way, how many number of transistors that we have used here? 1, 2, 3, 4, 5, 6, 7, 8. 8 transistors totally we have used, but A bar, B bar is also there. For that one, another 2 transistors, 4 transistors are required. Total of XOR uses 12 transistors. 12 transistors. XOR uses 12 transistors. Please remember this. Okay, some more implementations we will see in the next class. Some typical equations that we want to implement by using the transistors. So the gate exam also they are asking this question very frequently. You please understand this concept. So some more problems we will do in the next class. Thank you very much. I'm extremely sorry. We'll do it in the next class sometime.